2016. Bolukbasi and co-authors at Microsoft Research feed the standard word to avec embeddings a simple analogy. Man is to computer programmer, as woman is to blank. The nearest word in embedding space, homemaker. The model was not asked to hold that opinion. The model was not asked at all. It absorbed it from the data, and then offered it back with the confidence of a textbook. Welcome back to Lecture 10. Today, the bias problem. Because models are never neutral. They inherit the world their training data came from, and when you deploy them at scale, they inherit the world's shape onto every decision they touch. We are going to cover embedding bias, demographic disparities, some debiasing methods, and the gorilla incident that made this a public conversation. V3 showed how much your writing style leaks. V4 is the flip side. Not what your data says about you, but what the model's data says about everyone else. Bias in NLP is not a single concept. It is at least 3 separate technical phenomena, each requiring a different fix. And people talk past each other constantly because they are pointing at different ones. Today's puzzle. The model is technically doing exactly what we asked. It is predicting the next token accurately. It is retrieving the closest embedding. It is classifying with hyphone. So, where does the unfairness come from? Answer. The training data is a mirror of a world that was itself unfair. The model absorbs that shape and reproduces it. Sometimes it amplifies it, and the math is not the villain, the pipeline is. Today's 3 beats. First, embedding bias. Bolukbasi 2016. The vector geometry of stereotype. Why word2vec learned homemaker equals woman. Second, demographic disparities. Different error rates for different groups, face recognition, speech recognition, machine translation, and the gorilla incident. Third, debiasing methods. Why the honest ones are hard, why the easy ones do not work, and where the field is now. Beat 1. Embedding bias. Word2vec, which we covered in Lecture 5, trains word vectors so that words appearing in similar contexts land close together. On the internet, the word nurse co-occurs with feminine pronouns much more than with masculine ones. The word engineer does the opposite. The embedding faithfully learns that co-occurrence pattern. When you then subtract man from king and add woman, you get queen, beautiful. When you subtract man from computer programmer and add woman, you get homemaker, same math, different vibe. In 2017, Caliskan, Bryson, and Narayanan formalized this with the word embedding association test, WEAT. It replicates the classic implicit association test from psychology, but on word vectors instead of people. Career words are closer to male names than female names. Pleasant words are closer to European American names than African American names. The same stereotypes psychologists measure in humans show up quantitatively in the embeddings. That paper, Science, 2017, put the empirical evidence beyond argument. Bolukbasi's paper also proposed a fix. Identify a gender axis in the embedding space. Say, E minus she. Project every gender-neutral word onto its component along that axis. Subtract that component, job done. Nurse and engineer now sit equidistant from he and she. The team called this hard Debiasing. It worked on the WEAT scores. But, and Gonen and Goldberg showed this in 2019, the underlying structure was still there. The bias had been projected off the visible axis but was still recoverable from the neighborhoods. Cosmetic surgery, not a cure. Beat 2. Demographic disparities in deployed systems. This is where bias stops being a table of numbers and starts becoming a real harm. In 2015, Google Photos, applying an image classifier, tagged photos of black people with the label gorillas. The team could not find a clean fix. They removed the gorilla label from the classifier entirely. That was still their deployed solution years later. The training data did not include enough darker-skinned faces. The model absorbed that gap and produced an offensive, dangerous mistake at scale. In 2018, Buolamwini and Gebru published Gender Shades. They audited 3 commercial face recognition products. On lighter-skinned men, error rates were under 1%. On darker-skinned women, error rates were up to 34%. Same model, same task, radically different accuracy depending on who was in the picture. That paper, SEIT 2018, reshaped how the field talked about deployed AI. because a 34% error rate on any real user is a broken product. The same pattern shows up in NLP machine translation systems that assumeth doctor is male and the nurse is female when translating gender-neutral pronouns from Turkish or Hungarian into English. Speech recognition with error rates up to twice as high for African American English speakers as for general American speakers. Toxicity classifiers that flag African American English dialects at higher rates than standard English. Every one of these is measurable. Every one of these is deployed. Every one of these is fixable, but only if you go looking. Beat 3. Debiasing. The naive plan, just clean the training data, is a fantasy. The internet cannot be cleaned. Every subsample carries the same shape, so the field has developed layered mitigations. Data level, re-weight or augment underrepresented groups. Model level, regularize against bias metrics during training. Post hoc, calibrate outputs to equalize error rates across groups. Inference time, refuse or hedge when confidence is low. None of them is a silver bullet. Layering them helps. There is also a math level problem. Different fairness definitions actively contradict each other. Demographic parity, equal positive decision rate across groups. Equal opportunity, equal true positive rate. Calibration, equal predicted probability meaning. If the base rates in the world differ across groups, you cannot satisfy all three at once. This is called the impossibility result. Choldechova 2017, Kleinberg-Mullinghathan, Raghavan 2016. Pick one and know what you gave up. There is no neutral choice. There is only an accountable one. So, the honest state of the field. Embedding level bias is quantifiable and partly reducible but not curable. Deployment level disparities are measurable and largely fixable if you go audit. Fairness definitions conflict. That is a mathematical fact, not a political one. The practical answer is not ship a neutral model. It is ship an accountable one. Document your data, report subgroup error rates, let users appeal, and when you find you cannot make the model safe for a subgroup, hold. Do not ship the gorilla label. 3 takeaways before the quiz. 1. Word embeddings absorb the stereotypes in their training data. Bolukbasi 2016 named it. Caliskan 2017 quantified it with WEAT. The math is faithful to the internet, which is the whole problem. 2. Deployed systems produce demographic disparities. Gender Shades 2018 showed 34% error rates for darker-skinned women on face recognition. The gorilla incident showed what happens when nobody audits. 3. Fairness definitions conflict mathematically. You cannot ship a neutral model. You can ship an accountable one. Document data, report subgroup errors, let users appeal, hold if unsafe. Quiz 1. What did Bolukbasi 2016 demonstrate about word embeddings? A. That word-to-vec embeddings are perfectly neutral. B. That word-to-vec analogies encode stereotypes. Learned from the training text, man is to programmer as woman is to homemaker emerged unprompted. C. That embeddings only work for English. Or D. That embeddings can perfectly detect gender identity. B. The geometry of the vector space carries the co-occurrence patterns of the internet. Same math that gives you king minus man plus woman equals queen also gives you programmer minus man plus woman equals homemaker. Faithful to the data. That is the whole issue. Quiz 2. What did the Buolamwini and Gebru 2018 gender shade study find? A. All face recognition systems work equally well for everyone. B. Commercial face recognition products had under 1% error on lighter-skinned men, but up to 34% error on darker-skinned women. Same model, radically different accuracy across subgroups. C. Face recognition was equally accurate across genders. Or D. Face recognition was banned in 2018. B. The FACT 2018 audit put the disparity in unmissable numbers. Under 1% for the group best represented in the training data, up to 34% for the group least represented. Same model, different users. That paper reshaped the whole conversation. Quiz 3. Why does the field say you cannot ship a neutral model, only an accountable one? Because fairness is impossible to define. B. Because common fairness definitions, demographic parity, equal opportunity, calibration mathematically cannot all hold at once when base rates differ, so shipping requires choosing which trade-off you are willing to defend. C. Because models are always broken. Or D. Because accountability laws exist. B. Chuldachova 2017 and Kleinberg, Mulanathan, Raghavan 2016 proved this. When base rates differ across groups, the three standard fairness criteria are mutually incompatible. You cannot dodge the choice. You can only make it consciously and document what you gave up. Back to the puzzle. The unfairness does not come from the math. The math is doing exactly what we told it to. The unfairness comes from choices, of data, of annotators, of deployment target, of shipping decision, and that means it is fixable, which also means somebody is accountable for the choice not to fix it. Next video, the hallucination problem. Next time, why LLMs lie. Not because they want to, because they are trained to produce plausible text, and plausible is not the same as true. Definition, measurement, and why retrieval only partly helps. Hit subscribe.